ini everyone, and good evening to one and all. I'm Simi Shahudin, Secretary of IEEE SP SNIT, with my co-host Aishwarya S, PR Executive of SEEM SC SNIT. I'm very much honored to welcome all the dignitaries, guests, and delegates with great joy for today's section. This is our webinar section organized by the IEEE SP SNIT and IEEE IAS SP SNIT in collaboration with SEEM SC SNIT. Hope you'll enjoy.
Today's webinar is about grid modernization, renewable energy, and smart grid system. Smart grid technology is enabling the effective management and distribution of renewable energy sources like solar, wind, and hydrogen. So now to begin our session, I call upon Ashwin A, Chair of SEEM SC SNIT, to give the welcome speech.
Aishwarya, is it audible?
Yes.
Good evening, everyone. Myself, Ashwin A, Chair of SEEM Student Chapter SNIT. The whole world is fighting against coronavirus. In this time of vigilance, we need to make the most of the even limited circumstances before us. I consider it a great privilege to be a part of such a webinar on the topic Grid Modernization, Renewable Energy, and Smart Grid System. And I personally appreciate all the people in this meeting. It is my duty to welcome everyone who is in a part of it today. Our respected principal, Dr. Radhakrishnan R., who stand by all our activities with the presence and cooperation. Welcome, sir. Then I would like to welcome the esteemed speaker, Mr. John McDONALD, Smart Grid Business Development Leader at GE Solution, CIGRE Distinguished Member, IEEE Life Fellow, Past President, IEEE Power and Energy Society. Welcome, sir. Next, I welcome all the branch Counselor, Assistant Professor Karthika Nair, and Chapter Advisor Sri Lakshmi Nair ma'am, who stand by our activities with and cooperation. Welcome, ma'am. Next, I welcome SEEM Student Chapter SNIT Counselor, Assistant Professor Sharad Kumaras for his great support. Welcome, sir. Next, I welcome all the heads of the department. Welcome all. Next, I welcome all the executive members and all the members who work with us for the success and program. And those who have accepted our invitation and are warmly and respectfully welcome to this program. Before we get started, once again, I would like to express my hearty welcome to all who even come to this event together to make it success. May God bless you all abundantly. Thank you.
Thank you, Ashwin.
Thank you, Ashwin. Today's section will be conducted by Mr. John McDONALD. He has worked as a Director, Application Engineering, later EMS Business Unit Director at Advanced Control Systems. Then he has worked as a Manager, Substation Automation at GM Marketing, and he has worked as a Director, Technical Strategy and Policy Development at GE Solution. He served as a volunteer for more than 50 years at IEEE and is currently working as Smart Grid Business Development Leader since 2016 at GE Solution. We are very much honored to welcome you, sir. Sir, please.
Well, thank you. Can you hear me okay?
Yes, sir. It's perfect.
Okay, good. Well, thank you for the opportunity to be with you today. I really enjoy talking to student branches all over the world. I've always enjoyed that. I've always enjoyed traveling to see you in person, but with COVID, we aren't able to do that. So this is the next best thing, right? To be virtual. Let me share my screen, okay? And I'll bring up my slides. Let's see. Can you see my slide?
Yes, sir. We can see it.
Good. So thank you again. And I hope, if you have any questions, please at the end, hopefully we'll have time for questions, because I really enjoy hearing from you, hearing your comments or any questions you have. Now, I've been working in the smart grid area for 47 years now, full time, and this is my 50th year as an IEEE member. okay, 50 years in IEEE. So I've had many leadership positions, including the IEEE Power and Energy Society President in 2006 and 7, and on the IEEE Board of Directors in 2008 and 9, IEEE Standards Association Board of Governors, 2010, 11. And I've made many trips to India as an IEEE Power and Energy Society Distinguished Lecturer. My very first trip was in 2003 to teach courses in New Delhi and Pune. And I've taught courses in Mumbai at IIT, many.
Sir, excuse me? Sir, you are muted.
I wonder how that happened. So can you hear me now?
Yes, sir.
Interesting. So you could hear me and then all of a sudden it was muted. Okay. Can you hear me and can you see my slide?
Yes, sir. We can see your slide. It's audible.
Can you hear me too?
Yes. Yes, sir.
Okay. All right. So I was just going to say that this, I've been working in this area for 47 years, and this is my 50th year at IEEE, with many leadership positions. So grid modernization is actually the term that we use today instead of smart grid. I like it much better because it's actionable, right? We're modernizing the grid. Smart grid became a term that really lost its impact because everything seemed to be part of smart grid. So we like grid modernization better. And of course, one important aspect of grid modernization today is renewable energy. And then we'll talk about smart grid from the point of view of what was it that we were doing previously before smart grid in terms of adding intelligence to the grid, and what is it that we're doing today? Okay. One thing that I want to emphasize to all of you, particularly students, young professionals, is you need a balance in your life between your studies or your work and your health. Okay, it's very important. Make sure you get enough sleep. Make sure you eat healthy foods. Make sure you exercise on a regular basis. And I want to emphasize that because in the lower right picture here is my trainer. It's been 11 years now that I work out 5 mornings a week in a very intense boot camp. And my trainer was a professional American football player with the Chicago Bears and the Atlanta Falcons. And I've been working out with him again for 11 years and running 5K races. And I'll be 70 years old in December, but I'm stronger and in better shape than many of the younger people. Okay, so it's very important. Take good care of yourself. In the upper right is I'm with my son, who is a Georgia Tech electrical engineer in power. Worked for GE for 5 years and then got his MBA at Duke University in energy finance. And this was the morning after his graduation at Duke University with his MBA. And we ran the 5K trail on the Duke University campus. So we had just finished a 5K. It's called the Al Bueller Trail at Duke University. So anyway, take good care of yourself. The better health you have, the more exercise you have, you actually do, your work is much better. Okay, it's really an ecosystem of things that help each other. All right. I've been married 41 years, have 2 children, 2 grandchildren, And have always emphasized important with my family. And also, my wife and I love dogs. Many of you, if you know me, you know that I have a 4-year-old golden doodle named Bruno, who's laying on the couch right behind me here in my home office. And he's with me every second of every day. And we go on three walks a day. So these are the topics I'll cover. Again, if you have any questions, also, I'm going to reference some things. You know, I've written over 150 papers and articles. I've co-authored 5 books. One of the books is with Professor Minnie Thomas, who was a professor at Jamia Millia Islamia University in New Delhi, and she's now the director of the NIT in Trichy on a 5-year assignment. So Minnie and I wrote a book called Power Systems, SCADA, and Smart Grids that was published in 2015. That's one of the 5 books that I have. So when I reference papers or books, if you want copies or information about any of those, send me an email, okay? My email address is John D, so JOHN D as in David, .McDonald, McDonald, @ge.com. Okay, so let's get into the topics. First is key industry societal trends. You know, why is this important? Well, I mentioned a balance in your life between health and work. You also need a balance in your life between internal focus and external focus. If you're 100% internally focused, if you're the university student, you do your studies, and that's pretty much all you do. If you're working full-time, you go to work, you do your work, and that's all you do. That's okay, but you're not developing your career as much as you should. External focus is getting involved in like IEEE, but not just being a member, but taking leadership positions, right? Volunteering to be a leader, expanding your network of industry friends and contacts. That's very, very important because you learn a lot in your external participation, and particularly if you have a leadership position. And that actually helps you with your studies and it helps you with your work. You know, the 50 years I've been at IEEE, I've had many leadership positions. I've traveled all over the world. I have over 4 million miles on Delta Airlines. And I've learned so much in those travels, talking to people, understanding the differences around the world with technology, with business cases, with policy. And that's how you develop your career, okay? So you need to know what's happening in the world around you. And that's why I want to talk about key industry societal trends. If you're totally internally focused, you don't know what's happening in the world around you, the decisions you make for your studies, the decisions you make for your company with your work may not be the best decisions. In fact, they may be the worst decisions, but because you don't know what's happening in the world around you, you really need to keep in touch on a regular basis through industry participation and through your industry contacts, through your network of contacts. So what's the first thing, and I'll talk more about this, is we're transitioning from devices and systems to holistic solutions, okay? A holistic solution is very, very important. 2 very important words. Holistic means organization-wide, not just for one group in the organization, not just for protection, not just for planning, not just for power quality, but the whole organization, holistic. Break the silos down between the groups, bring the groups together. And a solution is what we're focused on today. It's a set of technology components from different vendors that are integrated together to successfully interoperate to meet the business needs of the customer. Okay, and I will show you in a minute 6 holistic solutions that are real that we're implementing in the field. And we have been implementing for over 10 years, okay? But we're transitioning from devices and systems. So a device is like a microprocessor-based device. Now, the very first microprocessor-based protective relay was introduced into the industry in 1984. Revolutionized the industry because previously we were using electromechanical devices, single function with no communications. So to read an electromechanical device, you had to go to the substation and do it manually. The revolution with these microprocessor-based devices, they're multifunction and have two-way communications, which means that they're not standalone. They don't have to be standalone. They can be a node in a bigger network, okay? And same with the system. Of course, systems have communications too. So one thing that's important, particularly for students and young professionals, is always think of the big picture. Don't just be happy with the device in the substation. That device has two-way communications. Yes, that device is providing value to the utility, but that device would provide much more value if it was a component in a holistic solution, okay? And I'll show you examples of those. Now, when I was leading the revision of the SCADA standard for IEEE in the early 1990s, and SCADA is supervisory control and data acquisition. So it's a very important industry term. I teach a course every January, a one-day course with a industry colleague, and it's called SCADA, the platform for all automation. Anytime you want to automate anything, could be the grid, could be a water system, could be a gas system, could be anything. The fundamental system, the platform that you need is a SCADA platform. Supervisory control means remote control. The data acquisition means acquiring data from the field, okay? A SCADA system has three components: a master station, field equipment to gather the information, and the communications that pulls it all together, okay? So again, I said Professor Minnie Thomas and we wrote a 350-page book. It was published in 2015 called Power Systems SCADA and Smart Grid. Very, very good practical reference on this. But SCADA is the platform for all automation, okay? So these devices, what we want to do is think of the bigger picture. Think of the holistic solution. And again, I'll show you examples of real ones. Success is, I say success, to be successful is really a three-legged stool, a stool with three legs. As you know, if a three-legged stool is missing one of its legs and you try to sit down, you'll fall over, right? You won't be successful. These three legs here, technology, standards, and policy, are similar. If you're missing one of them or one of them is very weak, you won't be successful. Technology, extremely important, but it must be standards-based. And there's two key words here. Holistic solutions is a key concept, but two key words are integration and interoperability, right? For technology to be able to be integrated and to successfully interoperate, it must be standards-based. And at the end of this talk, I'll talk about industry standards and their importance. That's why, truthfully, in 1987, I joined the IEEE Power and Energy Society Substations Committee. In the IEEE Power and Energy Society, there's 17 technical committees and 3 coordinating committees that write all the standards for the electric grid, okay? Now, in 1987, I joined the Substations Committee. This committee writes all the standards globally for substations. In 1987, I volunteered to become a working group chair. In the 90s, I became the subcommittee chair over all standards in substation automation. And in 2001 and 2, I was chairman of the entire substations committee. In fact, we wrote a book in the 2000s. It's the most practical reference book today in substations called Electric Power Substations Engineering. 22 chapters on substations, and it's in its 3rd edition. It's a very, very good reference on substations. But you really learn the technology and standards when you write the standards, because you write the standards about what's happening in the future, not about what happened in the past or what's happening today. And you're with many, many industry experts from all over the world. So, you know, you can imagine how much new things that you learn, and you become much more valuable in your career, but also to your company, okay? And policy is the strongest driver today to encourage a customer to buy my technology. So we spend a lot of time with people that make policy makers, to shape policy. I want the policy to be very strategic for me at General Electric so that customers will buy my technology. So we spend a lot of time with policy makers, okay? Now, a couple of important terms here is flexibility of the grid, self-healing, and being able to reconfigure. We have logic today that I can put on the distribution part of the grid that can automatically detect the fault, locate the fault, isolate the fault, and restore service upstream and downstream of the faulted segment, all without a human in the loop. That's truly a self-healing grid. And I'll show you how that works. Okay, I'll show you that in a minute. Next bullet is the word resiliency. You know, resiliency is how well the grid withstands stress. What do we mean by stress? Well, let's say that we have an extreme weather event. In India, you might have a monsoon, right? In the United States, we may have a tornado. We may have a ice storm, right? Like the state of Texas did several months ago. We may have a blackout, you know. We may have lots of different things that occur that really stress the grid. And it's a good measure of how resilient is the grid? How well does it withstand the stress? We do everything we can with redundancy and reliability, but the true test is when it's stressed, okay? So there's a lot of focus today on resiliency, and that's encourage people to do much more work with microgrids. We're putting in many, many more microgrids today to provide the grid operator more flexibility, and so the grid would be more resilient. We'll talk more about big data. What's exciting to me today is what's happening with what I call the journey, the digital transformation with the electric grid. This is an important part of smart grid today. We're hiring data scientists. Electric utilities are hiring data scientists, and we're focused on what's called an observability strategy. We'll talk about that in a little bit, about developing new analytics and about more artificial intelligence, machine learning, the concept of the digital twin, and the application of all of this in asset performance management, or APM. Now, I've mentioned two of the 5 books that I've done. One being Power Systems SCADA and Smart Grids. 2 being Electric Power Substation Engineering. One of my most recent books that I wrote the first chapter in is called Big Data Application in Power Systems. And I wrote the first chapter of the book called A Holistic Approach to Becoming a Data-Driven Utility. 2 key concepts there: holistic, right, organization-wide, and being data-driven, right? All your decisions are driven by data. So that book was published in 2018, just a few years ago. So we'll talk about that. We'll talk about automation platforms today, like SCADA systems have cloud components, public cloud components. And also we're encouraging utilities to use more social media. I would rather interact with my electric utility, not through phone calls, but through Twitter. I'd rather tweet outage information or tweet information to my utility, and they look at my Twitter handle and use my Twitter handle to pull up my customer record, okay? And then one thing very important today is convergence of the information technology part of the utility with operations, the operations technology, because we need a seamless working together of IT and OT to support enterprise data management. And that's very, very important. We'll talk more about that, okay? So I know that was, we spent some time on that slide, but there are fundamental concepts, trends that are really foundational to smart grid, okay? So I mentioned this, the integration of electrical and information infrastructures of the electric utility. IT-OT convergence, extremely important. This is part of something that I emphasize all the time in industry is before we think about smart grid, we need to make sure we have a strong grid, okay? Strong grid before smart grid. If you were gonna build a house and you had all the material to build your house and you went out to the site of your house and you had to have a concrete foundation and you look at that concrete foundation, it had big cracks in it, okay? Would you go ahead and build your house on a foundation with big cracks? Hopefully not, right? Hopefully you'd want to have a strong foundation before you build your house, okay? Similarly, you want to have a strong grid before you start adding a bunch of new stuff on top of it, okay? And a strong grid has two key parts. One is the communications infrastructure, right? Remember I said three key parts to any automation system is the master station, the field equipment, and the communications that pulls it all together. Another cardinal rule here, one is a strong grid before smart grid. Second one is communications is the enabling technology that allows us to automate, okay? So I learned as an undergraduate electrical engineering student in power systems. I love the automation of the grid. I've been doing it for 50 years, right? Adding intelligence to the grid. But I learned as an undergraduate electrical engineering student, I said, I have to learn a lot about communications because without communications, I can't automate, right? Automation is limited unless you really know a lot about communications. The communications infrastructure is important. And there's certain trade-offs with communications, wired versus wireless, right? And public versus private. Does the utility build the communications network and own it, private, or do they use a public carrier, okay? So these are all trade-offs, and the hybrid, the communications infrastructure today at any utility is a hybrid mix of wired, wireless, private, public, many different technologies all working together, okay? So the strong grid is the communications infrastructure and the IT infrastructure. We need IT and OT to be seamless, to work together. So otherwise we would have a disconnect in the enterprise, and it would affect us in the ability to do enterprise data management. We wouldn't be able to do it, okay? So if we can truly have IT-OT convergence, we can improve the utility's reliability, performance, productivity of the workforce, energy efficiencies, decreases in carbon emissions, so we help the environment. We empower consumers to manage their energy use and save money without compromising their lifestyle. This is something new with smart grid in the last 12, 13, 14 years. And I'll finish my talk with emphasizing this, is the consumer has become an important stakeholder in smart grid. We have to understand the consumer. We have to engage consumers. We have to segment consumers. And what I mean is not all consumers behave the same. Not all have the same desires. Not all have the same price points. We actually have 4 to 5 different segments of customers with very different characteristics. So if you're developing a program for customers like smart metering, right, as an example, or demand management, you can't assume that one program will satisfy every single customer because there's 4 or 5 very different segments of customers. And lastly is optimize renewable energy integration and enable broader penetration, okay? We're trying to integrate much more renewable generation into the grid, okay? One of the parts of the title of this talk. Now, with smart grid, there's much more focus on the distribution part of the grid, which is very important because the distribution part of the grid has had very little investment, not just for years, but for decades, okay? So Many of us, like myself, who have been, I started adding intelligence to the grid with my full-time work in 1974. So it's been 47 years. So the concept of smart grid is not new, right? The intelligence I was adding to the grid in the 1970s and 80s and 90s and 2000s, many of us were making a grid smart. So what's the difference with the term smart grid? I like to say what we're doing new is a smarter grid. Not smart grid, but smarter grid, okay? And what I show here in light green is the new stuff we're doing, and in gray is old grid, what we were doing. So you can see the legend on the right here in the middle. Old grid is shaded in gray, and smart grid additions in light green, okay? I could spend, days on this slide going over all these things in more detail, but we just, we don't have time. So let me highlight a few things here. You can see voltage control is shaded halfway. Well, I was doing voltage control in the 1970s, and it was for utilities. Like, let's say they were summer peaking, and then a hot summer day, they were approaching their previous peak, and they didn't want to exceed that because they would have financial penalty. So we could lower the secondary voltage, and voltage is directly proportional to load. So this was called load management, and we would do this through voltage control. In addition, to reduce losses, we would control reactive power, right, with capacitor banks, voltage regulators, and that was called VAR control, right, reactive power control. And for many years, we did these separately. So what the light green part of this is the fact that we're doing voltage control and reactive power control together. We call that integrated vol-VAR control, or we call it vol-VAR optimization, okay? We'll talk more about renewable generation. Let's go up to the middle here. You see sensors is shaded halfway. Well, we've been adding instrumentation to the grid for many years, but what's different today is we have a lot of specialized sensors, and that give us very, very valuable information. As an example, the sensor I'm showing here is, I would connect it to a transformer, and I would take the oil from the main tank of the transformer and have that oil go through the inside of the sensor. And the sensor can detect dissolved gases in the oil of that main tank. And this is called DGA, dissolved gas analysis. Very, very important. And we have sensors today that can detect up to 9 different gases in the oil of the main tank of the transformer. And the presence of a specific gas tells me the failure mode that's occurring in the transformer. For instance, if I see methane, or I see ethylene, or I see acetylene, these are all common gases that we may find, that the sensor may find in the main tank. That's a specific failure mode that's occurring, okay? And why that's important today is that we've moved in the journey to digital transformation of the grid. We've moved from being reactive to being predictive. Very important. We used to, for many years, wait until something failed, and then we reacted. That's kind of silly, right? Kind of stupid to do it that way, because you have equipment that you've lost equipment. It's been destroyed. It's failed. And many times, like a transformer in a substation would have what we call a catastrophic failure, and it would damage all the equipment in the substation with an explosion, with a fire, right? Why wait until something failed? Why not get health information on the asset, use analytics to predict the health of the asset and prevent a failure from occurring? That makes more sense, right? So that's what we're doing today. That's called predictive. And we use specialized sensors to give us that information. So what's important today for utilities is what we call an observability analysis. The utility, observability analysis and observability strategy is looking out across the entire service area of the utility and saying, what data am I getting back from every part of the service area? And am I getting all the data that I need? Why is that important? Because utilities are buying analytics, and I'll show you examples of analytics in a minute, but new analytics. That analytic can only optimize what it knows is happening in the grid. If we don't give the application or the analytic the information it needs, it won't be able to provide us all the benefits that it can potentially provide, right? It can only optimize what it knows is happening. So it's very important. This observability strategy is very important, you know, and that's why we have such a focus on data today, much more than ever before. Let's move to distribution management. I'll talk about this a little bit in terms of what we call a distribution management system. The distribution part of the grid is becoming much more complex with the integration of distributed generation. And we need a separate SCADA system to manage that complexity, and that's called a distribution management system, or we call it an advanced distribution management system, a DMS or an ADMS. Then we get out downstream of the substation on the feeders. This is distribution automation, and then smart meters, and we'll talk more about smart meters, okay? Smarter grid is what we're talking about. So this is examples of 6 smart grid holistic solutions. Now, I'm going to highlight them on this slide, but on the next slide, I'm going to show all the technology components around the utility enterprise that are needed for each of these 6 holistic solutions. And you'll see what I mean by the term holistic solution. So these are real. These have very strong business cases for electric utilities worldwide, okay? First one is asset optimization. So this is, again, what I just talked about was it's looking at very critical assets. First is transformers, and second is high voltage and medium voltage circuit breakers. And we're looking at the health, predicting when failures may occur, and then addressing those before the failure occurs, okay? This is probably the second strongest business case today of all these solutions. Very, very popular, lots of investment. And let me emphasize one other thing too with asset optimization. Since COVID in March of last year, we've all shown ourselves that we can do much more virtually than we thought we could, right? We could do much more from home, from a home office, than going to the office or even going to the field, going to the substation. What utilities are doing today is increasing their budgets for 2 things: monitoring and diagnostics of assets, we call that M&D, and secondly is asset performance management, which is utilizing the monitoring and diagnostic information to optimize the assets, okay? Why? Because we've shown ourselves we can do more virtually. Why do utilities need to have people go in a truck out to the substation when they can do much more remotely, okay? And so remote monitoring and diagnostics and asset performance management has increased spending today than before because of COVID, okay? And because of doing things virtually or remotely. So there's a lot of attention to this. Demand optimization is aggregating loads, aggregating demand, and we're actually using that as a dispatch tool in the control center for generation and transmission, okay? Third is smart meters and two-way communications, right? We're putting a lot of smart meters in, microprocessor-based meters. And what I'll show you here in a minute is we're using the information in smart meters to a great extent. In other words, smart meters have much more value than just the meter reading to generate the bill of the customer. Fourth is distribution optimization. And I said, there's much more focus on distribution than there was before. And this is actually the strongest business case today, has the most attention, the most investment of any of these holistic solutions. In general, for every dollar I invest in distribution, I get $5 to $6 back. So it's a very strong, what we call benefit to cost ratio. Fifth is transmission. We're doing a lot on transmission also, and particularly with respect to synchrophasers or phasor measurement units. Some of you may be doing studies, in your studies, maybe looking at PMUs. We call PMUs phasor measurement units with synchrophasors. The advantage of these, and we're putting them in many substations, is that we get 40 to 50 samples per second. So when we talk about SCADA data is typically every 2 to 4 to 6 seconds. But when we have 40 to 50 samples per second, we have a lot more insight into what's happening on the grid, right? And we can do things like transient stability analysis. We can do things that require much more detail, much more granularity in the data, because we have it with synchrophasers. And the lastly is workforce and engineering design optimization. One is standard engineering designs to save money, also to save time. And the other thing is the workforce. We need to have much more emphasis on bringing in young people into the organization, because in every country in the world, we have a situation like, I can tell you specifically in the US, in the energy industry, in the next 5 years in the US, 40% of the employees, so not just the engineers, but all employees, 40% of the employees and 60% of the executives will retire, okay? Now, I'll tell you, when I became president of the IEEE Power and Energy Society in 2006, we studied what we needed to do to increase membership in the Power and Energy Society. And it turned out that the average age of the PES member at the time was over 50 years old. And the average age of the IEEE member in general was 42. So, as a society, we had an older group. We really needed to attract young people. And so what we did in 2008 in IEEE, we changed the name of PES from the Power Engineering Society to the Power and Energy Society. And by energy, we emphasized, since 2008, we've emphasized that what we do is we help the environment, right? Particularly with renewables. We help society. We help the environment, as we talked about. And that's important. And it's very important to all of us, but particularly important to, to students and young professionals. And since we changed the name of PES, so the E in PES stayed an E, but instead of engineering, it became energy. We've grown dramatically since 2006-07 when I was president. And we now have over 40,000 members. We used to be the third largest society in IEEE. We're now the second largest society, second only to the Computer Society, okay? Now, another aspect of workforce is mentoring. Each of you as students or young professionals should have at least one mentor, okay? And I'll tell you why that's important. When you start working full-time in engineering, in industry, what we do, the work that you do is an art more so than a science, okay? And there's a big difference between art and science. Everyone can do the science by reading books, reading textbooks, reading books. That's what you do at the university. You learn the science, okay? But what we do in the real world with our work is not purely science, but it's the application of the science in the real world. And you can't read a book and know that art. That's called the art of the science. You have to spend time with experienced people day and day and day in the field, in the substation, in the control center, and learn how to apply the science in the real world. That takes time. And that's why mentoring is so important. You should have a mentor, at least one mentor. You should spend time with that mentor on a regular basis and learn the art of what we do. Extremely important. Can't emphasize that enough, okay? So let's take those 6 solutions, and these are the technology components. Remember, a holistic solution is a set of technology components integrated together to successfully interoperate to meet the business needs of the customer, okay? So let's, just as an example, let's take the light blue boxes here. These are the distribution optimization holistic solution. The 4 boxes, well, the upper left here is the office or control center. Lower left is substation. And lower in the middle is equipment on distribution feeders, switches and breakers or voltage reactive power devices, okay? Upper left here, these 4 blue boxes at the top are actually software applications running on the DMS, the distribution management system. Below that, the 2 blue boxes are systems, okay? The distribution management system and outage management system. The lower left in the substation, we see a blue box called applications. We actually take some of the applications from the control center and we run these in the substation. That's called distributing the intelligence. So we don't have to necessarily do all the calculations in the control center itself. We can distribute the intelligence. Now, the switches and breakers here, that's the equipment to support the logic of fault detection, isolation, restoration, FDIR. This is what gives us the self-healing grid I talked about in the beginning, okay? And VolVAR devices here are capacitor banks, voltage regulators. That supports the logic of integrated VolVAR control that we talked about earlier. Integrating voltage control and reactive power control, okay? So you can see how important integration, interoperability are when you look at all these technology components. And you think about this, these blue boxes are all from different vendors, but they all have to successfully communicate with each other and exchange information with each other. And that's not trivial. That's not easy. That's why standards, compliance to the same set of standards or the same standard is critical, okay? Now, the utility should invest, there's 5 key components the utility should invest in. Smart meters. AMI is automated metering infrastructure. This is the 2-way communications with the smart meters. That's number 2. Number 3 is the geographic information system. 4 is the outage management system. And 5 is the distribution management system, okay? And integration, interoperability, I said, are important. Well, smart meters, in addition to the meter readings, we ping certain smart meters to get the voltage, and we put that in the network model in the distribution management system. And when we do integrated VolVAR control, we flatten the voltage profile and then we lower it. Okay, that reduces, that helps reduce losses. And, but we have to make sure the voltage at the very last customer is within the limits. Every country has a standard with respect to what the voltage should be at the customer. And in the United States, it's 120 plus or minus 5%. It's an ANSI standard called American National Standards Institute. ANSI standard C84.1 in the US. So 120 minus 120 volts minus 5% is 114 volts. I have to make sure that, you know, when I do VolVAR control, that the voltage at that last customer on the feeder is above 114 volts. Very important. So I ping certain smart meters to get the voltage. And then smart meters all have the capability that when they have an outage, there's enough energy in the smart meter for one final communication upstream to the utility, and we put that information in the outage management system. We call that last gasp communication. In other words, your last breath, right before the outage, your last opportunity to communicate. The geographic information system is the reference system for the network model for the outage management system and the distribution management system. We take status changes from the distribution management system, and one example would be a distribution feeder breaker now trips. So that feeder is de-energized. We take that one piece of information and send it to the outage management system. It has the network model, so it knows now that feeder is de-energized, it knows all the customers that are connected to that feeder, and it knows now that all those customers have an outage. And then I mentioned with customers, we want to transition from phone calls to social media for the customer to interact with their utility. We did a survey 5 or 6 years ago at GE of utility customers in the US, and we found over 70% said they prefer to interact with their utility through social media, not with phone calls, okay? So let's look at microgrids and distributed generation. One of the things with the distribution part of the grid that I say at the bottom of the slide is we designed controls and protection for the distribution part of the grid to take advantage of electricity flowing in one direction, which was the case for many years. The distribution part of the grid had electricity flowing from source to load only. So if you work for a utility and you were going to go out in the field and do maintenance, you knew that if you opened the upstream device, you always had a safe working condition because electricity flowed in one direction. You open up the upstream device and you de-energize the rest of the feeder, right? Well, that's not the case anymore, right? We have a wide array assortment of distributed generation that we're integrating to the distribution part of the grid. And it gives us unique challenges that we'll talk about. Two-way flow of electricity and concerns with voltage regulation. So, if you look at the grid from generation, the switch yard right outside the power plant, right? That's where we step the voltage up. As you know, we can generate at say 11,000 volts, but to transmit the electricity, if we have to raise the voltage substantially to minimize the losses, right? Remember, power is voltage times current, but losses are a function of the square of the current. So power is voltage times current. If we can raise the voltage substantially to send that same amount of power, we can do it with a lot lower current, right? E times I, raise E, lower I, and losses are a function of I squared. So it greatly reduces the losses. So the generation switch yard, right? We take the generated electricity, we up the voltage substantially, right? And then we can transmit that over long distances with lower losses. We get into transmission substations as we get closer to the loads. We step the voltage down for distribution substations, and then we get to the end user. Could be industrial load, could be a residential load. But we're integrating renewables now at the transmission level, right? Large wind farms at the distribution level and at the end user level. And at the end user, we see a lot of photovoltaic panels, right? Rooftop solar. So we'll talk about that. So it's more, that's what I mentioned about distribution management system now is needed to manage the increasing complexity of the distribution grid. two-way electricity flow, and additional challenges I'm showing on this slide. Open circuit over voltage due to unintentional islanding. What's really critical is protection ratings may not match fault currents. Okay, why? Well, when you're doing a protection study to determine the settings for the relays, you have to do a short circuit study first. You have to know what the anticipated fault currents will be at different parts of the grid. Well, when we did a short circuit study, we typically assumed only a source side contribution to the fault, only. But as we integrate and as the penetration of distributed generation increases, we have a greater contribution to the fault now from the load side. But when we set the relays and did the short circuit study, we typically only looked at the source side contribution and determined the protection ratings that way. Well, that's not accurate anymore, right? And also the fault currents due to the distributed generation vary, which makes it even more complex because of the intermittency of the distributed generation. The wind isn't blowing all the time. The sun isn't shining all the time, right? So the contribution from the load side is varying. And we'll talk more about the stress on voltage regulation equipment in a minute, okay? So one of the things, I mentioned this with respect to resiliency also, is much, much more attention to microgrids. And this is a microgrid project we did in Canada. And originally microgrids were had primarily three applications. University campuses to do a better job of efficiency of electricity throughout the campus. 2 is military bases. And 3 is rural villages. Rural villages, a village that isn't near any electric utility, right? It's not near an electric line, not near a utility. This was a microgrid. This is a microgrid because it's operating today for a rural village in British Columbia, Canada. And you can see that it has industrial load, that there is industrial load and there is residential load. But they have, in the village, hydrogen fuel cells, some solar generation with PV panels, and some low head hydro generation. And typically with a rural village, the base generation is diesel, right? Diesel generation. So how can we satisfy the load continuously, minimize the use of the diesel because the fuel is very expensive to transport to a rural village. And also it pollutes, when a diesel generator operates, it sends carbon dioxide to the atmosphere. So we took a microprocessor-based relay in the upper left here, a U90 microgrid, and we added logic to that relay to become the microgrid controller. So its objective was to make sure the load was satisfied continuously, minimize the use of the diesel, maximize the use of the other resources. And these blue boxes here are all high-speed communications devices. So we were looking at, data on a continuous basis, right? So this has been very successful. This is called Bella Coola Village, rural village in British Columbia. Now, I mentioned the intermittency, with solar, the sun's not always shining. With wind, the wind's not always blowing. So how do we compensate for the variability? Well, we have bridging storage. Energy storage, we use to bridge those gaps of intermittency. We also have fast start thermal generation. Natural gas fired turbine generators that can start fast and also respond quickly to changing conditions and system frequency. And in fact, because the penetration of renewables continues to grow, we're seeing new technology solutions here for the compensation of the variability. One example is at GE a couple of years ago, we announced a new electronic gas hybrid turbine, which is a package of 10 megawatts of lithium-ion batteries and a 50 megawatt natural gas-fired turbine generator in an integrated package with software that optimizes the integrated operation of the batteries in the turbine generator. And that's been used widely by utilities, again, to give you two things. You know, one is instantaneous support for system frequency when the solar generation goes away and the wind generation goes away, but also support for longer term with the turbine generator. The batteries, good for instantaneous, turbine generator, good for longer time frames, okay? Now, one thing with smart grid, the smarter grid, okay, is you think about the controllers we've been using in the grid for many, many, many years. Many of these controllers are mechanical, which means that the more frequently they operate, their life, right, their expected life decreases, right? They wear out. That wasn't a problem, has not been a problem until we started integrating renewables. And due to the intermittency of the renewable that affects the grid and adds volatility to the voltage and reactive power. So here's a specific example of that. And this article is available, even though I wrote this article almost 8 years ago, it's available online. So you can search for Power Electronics Magazine and my name, and you'll see this article. And the very beginning of the article, I include the voltage waveforms on a distribution feeder in San Diego. And we got this information from San Diego Gas and Electric, from the electric utility, because they were faced with a situation they had never seen before, and they weren't sure what to do with. Think about this. Here's a distribution feeder that has a online tap changer in a substation, right? That's mechanical. And the goal of the tap changer is to keep the secondary voltage constant. So as the primary voltage fluctuates, the tap changer changes tap settings to keep the secondary voltage constant. So the tap changer will typically have 16 raised positions, 16 lower positions, and a neutral position. And each position change is a change in 0.5% of voltage, okay? But the more frequently this tap changer operates, again, it's mechanical, okay? So typically on this feeder, the tap changer would operate maybe 5 times a day or 10 times a day, typically, okay? Now the policy in California changed, and the policy makers said, okay, as a homeowner, if you consume electricity, you pay 10 cents per kilowatt hour. But if you put solar panels on your roof of your home and you're generating electricity and you sell that electricity back to the utility must pay you 40 cents a kilowatt hour. 40 cents, 4 times what you pay to consume electricity. Well, this business case was very attractive. And many residential homeowners invested in putting rooftop solar panels on the roofs of their home. In fact, this happened so quickly that on this one feeder I studied and wrote the article about, this one feeder, over 35% of the homes on one feeder had rooftop solar panels. These are beautiful homes along the Pacific Ocean. And in the morning, they would have a marine layer of fog, right? Fog that was caused by the moisture in the air with the ocean. And then as the morning became closer to noon and early afternoon, as the morning continued and the sun came out, the fog would eventually burn off. So at some point late morning, all of a sudden, all of these homes would begin generating at the same time. You should see the voltage on that feeder. The voltage spiked, right? And then it oscillated widely as the sun went behind the clouds, and all of a sudden out from the clouds and the generation started, then behind the clouds. This poor tap changer in the substation started operating each day well over 120 times, okay? Its expected lifetime went from 35 years to less than 2 years, okay? It would have to be replaced. So, my point with writing this article in Power Electronics magazine is we have new applications of power electronics in the electric grid caused by the impact of high penetration of rooftop solar PV, right, photovoltaic, on the distribution system. The tap changer is one example. Second example is a new family of low voltage power electronic controllers that we're putting on the low voltage network. So we call these low voltage network dynamic because it's continuous set point control, grid edge controllers, okay? And the third is what we call smart inverters, increased capability from inverters. So again, the impact of distributed generation, particularly on the distribution part of the grid, that it creates tremendous volatility in voltage and reactive power, and we can't use mechanical controllers in the future. So at universities and at companies, the power electronic students, the power electronic researchers, the power electronic professors need to work closely with the power system students, young professionals, professors, work together, because we really have we need new applications of power electronics on the electric grid, and this is low voltage power electronics, okay? So this is why in the IEEE we have a Power Electronics Society and we have a Power and Energy Society, and these two societies need to do more things closer together, okay? Now I talked about the distribution management system, and I said, we can call this the Advanced Distribution Management System, ADMS or DMS. And this is the centralized control model. So this is where all the decisions are being made in the control center. So all the information from the field is coming into the control center. And the ADMS has two parts, a basic SCADA platform that does supervisory control and data acquisition, and then all the applications that optimize the grid. Okay, these are different applications, which I'll show you in a minute. So within the dashed lines here is the ADMS. On the right is the substation and feeder devices. That's the field. So the information, what's happening in the field, comes upstream to the ADMS. Then it calculates, it models, it optimizes, and all the control commands to do optimization then go back to the field substation feeder devices to do optimization. On the left, we show the geographic information system, which again is the reference system for the network model. So if you after COVID and when we start having in-person IEEE PES meetings and conferences, I teach, along with one other person, I teach a full day tutorial just on ADMS, okay? And we teach that at many IEEE PS general meetings and IEEE PES T&D conferences. So if this subject is something you want to learn more about, look for our tutorial, okay? It's also online, and you can, it's on the IEEE PES Resource Center, and It's 5 different PowerPoint modules and about 7 hours of material for a 1-day tutorial. Okay. Now the question is, what are these applications server? What are these applications? There's 3 groups of applications, and in the tutorial we go over each of these applications in detail. But this is the group of real-time applications that the operator uses all the time, continuously, to monitor and control the distribution part of the grid. Okay. Don't have time to go over these individually in this talk, but each of these is very important. And again, we cover these in detail in the tutorial. The second group is on-demand applications for analysis. So these are advanced analytical applications. And the third group is what we call extra or ancillary applications. Okay. Now, I talked about the utility doing the journey to digital transformation, right? Very, very important. But the question is, where is the utility today with respect to automation? How advanced is it? How much investment have they made? And typically, they have several steps that they need to go through to get to a fully digitally enabled grid, which is the goal of electric utilities today. So we need, no organization, no utility can do this in one step. They don't have the budget money to do that, but also they don't have the people resources to do it. So what we do is let's put a roadmap together, a strategic plan for how we can help the utility get there in steps. So here's a utility here that today is with manual control and legacy methods. A manually operated network and a static view of the network configuration, not a dynamic view. Okay. So let's take the first step, which is remote control and monitoring. So we've added SCADA, we've added trouble calls, we've added smart meters, and we've added circuit reclosers. So now they have 28% lower customer minutes interrupted, which means their distribution grid is much more reliable. Okay. Now the next step is automation and visualization. We had distribution automation, network visualization tools, and outage management prediction analysis, now at 43% lower customer minutes interrupted, much higher reliability. Okay. And then we're fully digitally enabled. Benefits are much greater than 50% lower customer minutes interrupted. And here we get into network optimization and utilization, asset performance management, and outage analytics, and distribution automation with power flow analysis. Okay, so in the real world, you can't do things in one step. You have to put a roadmap together. What's important with a roadmap is at every step, there should be significant benefits to the customer. Okay. Now another example here is a utility that says we want to improve our reliability, but we have a limited amount of money. So let's make the best use of the money that we're going to invest. Well, this is a large utility here. There's 856 distribution feeders or circuits. That's a lot. And let's study this and say, really, how much money do we need to invest? Well, when we studied it and looked at each of the circuits, we found that 23% of the circuits, or 200 circuits, contributed 71% of the total outage minutes. That's very, very important. So we don't need to automate all the circuits. That would be a tremendous amount of money. Initially, let's just automate 23% of the circuits, and we're addressing almost 3/4 of all the outage minutes. Very, very good return on investment, right? Very smart approach to do. They can greatly improve the reliability by spending the minimum amount of money. Okay, only 23% of the circuits. Okay, so to get more value out of the microprocessor-based devices, and again to get more return on the investment, we really have to look at types of data. Okay, there's more than just one type of data. And this information is from an article I wrote in 2003 in IEEE Power and Energy magazine. This is a magazine that all PES members receive. It's published every 2 months. And this was a 10-page guest editorial that I was asked to write. And I introduced new concepts to the industry that are today industry standard, okay? And what these concepts are that within an intelligent electronic device, again, this is a term we came up with in the 1990s when we were updating, when I was leading the revision of the SCADA standard at IEEE PES, was a microprocessor-based device. The IEEE term is Intelligent Electronic Device, or IED. There's two parts to the definition. One would be that it has internal processing capability, but secondly, it has two-way communications. This is important. Remember, I said we want to transition from a device and system to a holistic solution, and it's using the two-way communications. So I talk about operational data. That's common, but what I introduced was the concept of non-operational data, and that was new, okay? Operational data is something that we focused on for many years. It's the information from the field that we send to the control center. So the operators, they know the real-time status, the performance, the loading of the power system equipment. It's the fundamental information used by system operators to monitor and control the power system. And these are points. These are like current, voltage, real reactive power, circuit breaker open close, alarm information like high temperature, low pressure, intrusion into the substation, stuff. This is all points and status points or analog points, okay? The non-operational data is both points and files, data files. The primary user here is someone other than the system operator. And this isn't real-time information, this is on-demand information. So it's called non-operational because the operators aren't interested in it typically. And examples would be like a digitized waveform from a relay that the protection engineer would need. Maintenance information, the circuit breaker contact wear indicator. In a protective relay is the I²T information about the circuit breaker the relay is connected to. Or maintenance information, dissolved gas and moisture content in the oil of the main tank of the transformer that we talked about. So this is both points and files, okay? So operational data is typically individual time sequence data items, and it's typically a time series of points at the scan rate of the SCADA master. The non-operational data is points or a file. The operational data is real-time or near real-time. Non-operational is typically historical, a trend over time. Okay, operational data we communicate using standard communication protocols, non-proprietary, and non-operational data is points or a file. And if it's a file, we may need the vendor-specific proprietary format to access that file, okay? So let's look at big data. We talked about in the beginning, analytics and enterprise data management. So I'm sure you've heard the term Internet of Things, IoT, and it's really the next productivity revolution. We're connecting intelligent machines where we're leveraging technology and communication to cost effectively connect the machines with big data and analytics, okay? And
90%.
Combine the power of big data, big analytics, and industry physics. And we're connecting these with people, connecting people any place, any way, anytime for intelligent operation. Now, this connection is done through communications, right? And that's why there's such an emphasis on the communications infrastructure, okay? So the result of this will be more data, new analytics to provide new value, and people will have the data they need much more quickly, and they can make much better decisions then because they'll have the data they need for those decisions. Now, on the left side here is the current situation with many organizations where it's siloed. They have their own systems, their own devices, and their own data repositories. And on the right here is where we want to bring everybody together, what we call the holistic solution, right? Enterprise data management. We have a federated data mart in the enterprise. We're bringing together systems, devices, and repositories, and we're truly sharing data. So all the operational users, the operators in the control center have the information they need. But more importantly, the non-operational users, and this is 25 to 30 different groups in the utility, have the information they need. Very important. And to do this, on the left here, we're showing a standard architecture in a substation with a slave data concentrator talking downstream to microprocessor-based devices, and a master data concentrator collecting all the information from the slaves. On the right here in cyan, or the color light blue, cyan, is all the data sources in the enterprise. And in green are all the users, operational users, non-operational users. And ideally, they now have all the data that they need to provide the most value to the utility. So I'll summarize this journey to digital transformation. You know, this is really exciting. And to me, the ideal background a young person could have today would be a data science background and a power system background. We're hiring data scientists today and teaching them about the electric grid. And they're providing us much more insight and new ways of looking at the grid from a data science perspective, okay? So I said we started with reactive. So you look at the lower left here, we started with reactive, waiting for something to happen, waiting for something to fail, waiting for a phone call, you know? We didn't know there was an outage until a customer called. Then we went to responsive, and today we're at predictive. Okay, we're you know, what health information do we need? How do we analyze that health information? How do we predict failure? You know, do we have enough health information to predict all the failure modes of this asset? And we're learning much more about predictive, but we're only halfway in the journey. Next is prescriptive and then autonomous. And this is why we wrote the book, Big Data Application in Power Systems, because what we wanted to show in the book was how we can move to autonomous with more artificial intelligence, more machine learning, and using the digital twin. This was really exciting. If I was a young person today, I would print this. I would take a copy of this slide and have it in my office, or you know, my home office, because this is really the future, and this is really exciting what's happening today. So let me finish here with standards and then lessons learned. So standards are extremely important. You saw that technology roadmap, all those light blue boxes from different vendors. How do they successfully communicate with each other? You know, they have to have the same bit format of communications. So these two slides, this one and the next one, we're going to talk about standards. First thing is with smart grid, if you know, the landscape of smart grid is turbine to toaster, from the power plant to your home, right? Everything in between, generation, transmission, distribution, and end-use customers. If I gave you a sheet of paper and a pencil, and I said, draw all of smart grid on that one sheet of paper, what would you draw? Well, this is what we came up with. I chaired the board from 2010 to 2015 of 25 industry experts in the US, that we were responsible for all the smart grid standards work for the United States and harmonizing that with other countries in the world, okay? We had agreements with, you know, the India Smart Grid Forum, with the Japan Smart Community Alliance, with Korea, with European Union, all working together. And what we came up with was the smart grid conceptual reference model of these 7 domains on the left here, and how they're connected together with secure communication interfaces and the blue lines, okay? Now, that was important because it gave us a high-level feeling, a view of all of smart grid. But what was really complicated was IEEE said, well, we have over 100 standards involved with smart grid. And the IEC said, well, we have over 100. And that was a lot, you know, that's a lot of standards. There's too many standards for any person to understand or go through. So what we did was we looked at all those standards and we said, we need to get a smaller number of standards that's manageable, that's easier for people in the industry to use. And so on the right here is the foundational set of smart grid standards. There's 16 standards that are foundational to smart grid. And all you have to do is concern yourself with these 16, and you'll have the standard or standards that you need for what you're doing, okay? And what's really makes it easier too is, let's look at 3 levels of the electric grid, 3 hierarchical levels. Control center to control center, there's one worldwide standard. We call that Inter-Control Center Communications Protocol, or ICCP, for one utility to the control center, one utility to communicate with another utility. Second is control center to field equipment. There's really 2 standards in the world that are used. One is with North America suppliers, and that's called DNP3, Distributed Network Protocol 3, which is also IEEE Standard 1815. European suppliers prefer to use IEC 870-5-101 for serial and 104 for network communications. Now, if we're within the field, IEC 61850 is the worldwide standard for substation automation and protection. But in North America, we still use a lot of, as I said, DNP3 or IEEE Standard 1815 for substation and feeder device automation. So let me finish with a few slides here, and then we can have questions. After 18 months, a year and a half of deploying smart grid projects, we stopped and reflected back, and we said, what did we learn? What changes do we need to make going forward? So think about that technology roadmap slide, all those light blue boxes. A lot of different components are integrated together for that smart grid solution of distribution optimization, right? Well, what if one component isn't working properly? That whole solution then wouldn't work, right? So what's important is component technology is only as mature as the least mature component. In other words, if you take a chain and you pull the chain and it breaks, a chain is only as strong as its weakest link, okay? So when you put components together, right, for a smart grid solution, you really got to look at the maturity of each component. And in many cases in the field, we'd have to re-engineer or upgrade components to meet objectives and expectations. Because the real test for technology is when you get it in the field. You can test it in the factory, but the real test is when you put it in the field. Second is integration and interoperability. 2 key words. We really saw how important standards were in compliance to standards and interoperability. Third is testing. Not just testing in the factory, but end-to-end testing. From the device in the substation all the way up to the control center or the office, okay? Now, the other thing is project management. We found that, you could have the best engineers on a project, but what's really critical is a very, very, very good project manager. And that project manager needs to have authority over all the groups involved in the project. We call that multidiscipline authority. So there's two parts to being a manager. One is having the responsibility to do the work, but the second part is having the authority over all the groups involved to be successful, okay? Responsibility without authority is very frustrating. You have the responsibility, but you're not going to be successful, okay? You need both. And so we found that the project manager for a smart grid project really was critical and needed to have multidiscipline authority. And all the project managers need to have consistent project management guidelines, and there needs to be a program management office, okay, to have consistent project management, like communications among the team, status reporting, risk management. And really what we found was we as a supplier could have the best technology in the world, and we want a successful project with our customer. And the customer could have the best engineers on the team, but if the project manager was weak, the project could fail, okay? So we really need an A team, build an A team, the very best team of project managers and technical people, engineers, because there will be challenges to collectively solve as a team, especially when you put the equipment in the field, okay? And then I'll finish with, I mentioned this, I'm going to emphasize it again, that the residential commercial customer, the end use customer, the consumer, is a major stakeholder, a major part of any smart grid project, okay? For example, programmable communicating thermostats, in-home enabling devices, all these policies to incentivize customers to do home energy management. Two-way communication with the utility, intelligent thermostats, using Alexa at home, right, to control lights, using the GPS on your smartphone integrated with your intelligent thermostat to conserve energy. This stuff is all happening today. And you can save 15 to 20% per month on your electric bill by doing this, okay? So that's an important thing that we learned is we really have to focus on the end use customer. Very, very important. Okay, so that's the end of my prepared material. Lots going on. Let me, I'll stop sharing and we'll go back to the original screen. And if there's time, I'd be happy to take any comments or questions that people have.
Hello, sir. Hello.
Yeah.
Hello, sir. Can you hear me? Am I audible?
I can hear you. Yes.
Thank you, sir. Thank you. First of all, let me thank you for this wonderful class. So I would like to ask you something that you told us that reading some books are just science, and in the real world we are using the application of science, and that is called art of science. But according to our educational systems, we all are moving on with the old education systems still now. It should be upgraded. So is there any methods to change this? And next one is that nowadays everything is becoming virtually connected. So becoming everything virtually connected says that there will be a latency in a transferring of data. For example, the Formula 1 races are now transferred using a big underwater tunnel to provide the world feed for, during this Corona period. So they did not use the method of transferring it through air. They used the method of transferring it through underwater tunnel. So there will be a latency for providing the exact number of samples that we needed to provide for predicting the required energy. So how will that be how will that problem will be specified in our case?
Well, so there's two questions. The first question was, I emphasize the art over the science, and I really mean this. And as a student, you can help yourself by getting, looking for opportunities while you're a student to work with companies, right? I don't know, internships, co-op sessions, internet, post-COVID, international studies, going to another country for a semester to study, and we do work with companies. So, if you can get real work experience while you're a student, that's very, very valuable, because you start learning the art while you're a student. And any work experience you can get while you're a student, because I did this myself. After my first year of studies in electrical engineering, I had a summer job with a consulting engineering company. And my work, they really liked my work, and they said, John, anytime when you're home for Christmas, you're home for any holiday, and you have like a week or two, please come and work again, because we like your work. After I did the work, when I came back to school, I was a better student, because when you have some experience in the real world, when the professors are teaching you, you have that experience from the real world, and the things the professors are telling you, you really know what's important to really remember for when you start working in the real world, because you have some of that experience already. Okay, so you really want to look for opportunities. The other thing is, even virtually, I give many seminars to students as part of their engineering classes. I teach at Georgia Tech. I teach at the University of Tennessee, Chattanooga, 2 courses. I don't teach the whole semester, but the professors say, John, could you teach maybe 2 classes and teach how we apply these concepts in the real world, okay? So talk to your professors and say, can you have industry people contributing to the curriculum, to the content, to the lessons we learn, and help give us an idea of how we apply these concepts in the real world. The more experience you get in that way, you start developing the art yourself, okay? So look for work experience, look for like internships, co-ops, look for bringing more industry people into your curriculum. In the IEEE on the Resource Center, we have many tutorials, we have many online talks, and I have many of my own online webinars, courses on the IEEE Resource Center, the IEEE Smart Grid portal, and IEEE Educational Activities that's available to anybody online. Take advantage of these. This is what happens in the real world. So you have to take the initiative yourself. There's a lot of resources out there that can help you. Okay, that's the first one. The second one is the reason that there's latency. Okay, would be we didn't plan for COVID, right? We weren't really prepared for COVID, and we started having to do things virtually without really preparation. So we're doing things virtually using the same communications infrastructure that we've had previously. One of the reasons there might be more latency is we didn't design the communications infrastructure, say with the bandwidth or with the response, to handle the load that we have now with people, right, and data, because of so much virtual operation. Okay, so I think in time, as we do more things virtually, we will improve the communication system, to reduce or eliminate that latency that we have today. Okay, we were caught surprised with COVID, so we we will improve the communications, and we will improve the analytics. We will improve things so that the response requirements that we need, the bandwidth requirements that we need, and the amount of latency that we can withstand or tolerate will all be better in the near future, because we'll do more planning and we'll have the time to do it. Okay, we were just we were all very surprised with COVID and what we all had to do virtually, and we've done a good job, but it may not be the ideal situation, but we will improve things as time goes on. Okay.
Okay, sir.
Thank you for those two questions.
Sir, thank you, sir. I would also like to add on that sir said that we can save our electric bills about 15 to 20% by using the method of virtualization. But according to a developing country like India, there is a lot of problems in producing electricity for our whole nation. So how can a developing country like India and other countries can meet up this problem? And also, there would be some health issues by using these virtual problems by increasing the number of bandwidth. For example, when 5G came to India, there was a big problem that all the birds were killed by the radiations coming out from this bandwidth. So how will that problem solved?
I didn't understand you at the very end. What was the problem again?
Sir, sir said that our virtualization will be more advanced by taking time and by pre-planning. So, like a developing country like India, there are lots of number of people here. So, if we introduce a large bandwidth here, there will be a greater vulnerability for creating health problems in our nation. How will that problem will be solved?
You said by increasing bandwidth, it would affect the health of people?
Yes, sir. By creating a radiation, there will be health problems.
By creating radiation?
Yes, sir.
Oh, well, I can address that right away. There is no. A lot of groups around the world have studied the radiation from like smartphones and similar equipment, and there really is no proven, there's no connection between the radiation from a smartphone or transmission lines or anything like that affects people's health. So I don't believe that. I don't see there. I haven't read any science that supports that. So I wouldn't be concerned about that. Okay. And I forget what your first comment was.
Sir, first question was, sir said that we can save almost 15 to 20% of our electric bills by using the method of virtualization. But in a developing country like India, how can this be feasible? Because there is a large amount of voltage fluctuation here. So the equipments will be destroyed without getting the correct voltage input.
Right. There's things that in every country we have different situations. There's different technology available, and all you can do is you can do the most you can with conserving electricity. Depending on the technology you have available, depending on the money that you have available, the funds that each family has, and also what you're capable of doing. Okay, so things like you just do the best you can. But let's just say that the trend, right, is to what we all want to do in the world is empower the consumer to do a better job of managing their own energy use without compromising their lifestyle. That's our goal. Now, the ability to do that, you're right, it's different in each country in terms of the development of the country, the technology available, how much money the family has, what the priorities of spending are for the family with young children and things like that. But, the goal is to have that technology available, have the support available to help you, depending on what you would like to do. Okay, so I understand what you said, but I would say that all of us can probably do some conservation. All of us probably we waste electricity. We may leave lights on in a room when nobody's in there, right? Where we could turn the lights off. We may, with heating and cooling, the idea is we should all be as careful as we can be with conservation and with efficiency, energy efficiency. And just try to do the best job of using electricity wisely, right? As technology becomes available, if we want to use that technology to help us conserve even more, if we can afford to do that, we should do that. Let me get back to a previous point because I see there was some comments on that. I've read studies by the Electric Power Research Institute that in detail studied the radiation from a smartphone, a very detailed study, and also studies with transmission lines in terms of saying that animals that are in a farmer's field under a transmission line, like a cow, doesn't give as much milk as if it might be affected by the radiation from the transmission line conductors. Things like this, these are all been things that people have said, but when you look at the studies that were done, real scientific studies of animals, farm animals near transmission lines or smartphones, there is no concrete evidence that I've read in science that says that, that like radiation causes cancer, affects your health, like from a smartphone or from a transmission line. Okay, so that was my point. There's no link. There's no scientific evidence in that case, and I have many articles and many reports that I've read in that regard. Okay, so that's what I, because this is something that's very, I have a family, I have children. They don't live at home anymore, but when they lived at home, I was very concerned. I want the health of my family to be good. I don't want to do anything that would jeopardize, right, or adversely affect the health of me, my wife, my son, my daughter. So I've always studied, and being an electrical engineer myself, I've always read all of the scientific reports and studies because it's been a concern of mine. But I haven't seen anything that is concrete evidence in that regard. Let's give others an opportunity to ask questions.
Yes, sir. Good evening, sir. Good evening, sir. Thanks for that insightful lecture.
Yes, I can hear you.
Yes, sir. So my question is, you talked about unintentional islanding in one of your slides, but I read many IEEE papers where the probability of occurrence of unintentional islanding is very, very less. I mean, in some papers, it has claimed to be less than 1%. So it's a pure protection issue, whether we need to give importance to those issues as compared to intentional islanding, where we vouch for reliability of the grid.
Right. Well, all that we're saying is that it may be a low percentage. It's mostly it may be a low percentage, but let's say when it does happen, we don't want it to cause a real problem on the grid, right? You can't really say that unintentional islanding will never happen, or you can't say that I guarantee that this will ever happen, right? Because in the real world, there's always a small chance that something could happen. So you have to be prepared, right? And even though it's a low percentage, when it does happen, we don't want a blackout, or we don't want a serious problem to be created on the grid. It could be an over voltage problem that trips other devices, right? So we have to model that, we have to study it, and we have to make sure the grid is prepared for it, even though it may be a low percentage. If it happened to occur, we don't want it to create a serious problem, right? So we have to think of all the permutations, all the combinations, all the possibilities, model those, study those, and make sure we're safe, make sure we're stable, make sure we're reliable, make sure we're within voltage limits, right? Current limits, real interactive power limits, and that the grid is safe. So
yes, thanks for your insights, sir.
Have to be prepared.
Thank you, sir.
Okay.
Thank you, sir. Participants, this is a doubt clearing section. Anybody has any more doubts, you can ask now. Okay, sir, there is a doubt in the comment section. Okay, ask.
So can you hear me?
Yes, you can ask.
Hello, sir. Can you tell me some methods to mitigate the problem in integrating the solar or wind or other renewable energy sources which are being provided to the grid? There are some issues because of the uncertainties of the from the wind and solar. We are getting different values. So how can there will be some methods? Mm-hmm. So can you tell me about that?
It depends where the solar is connected into the grid. Okay, remember there were three possible interconnections, right? I mean, in general, one would be at the transmission level where we could have there's two types of solar in general. There's photovoltaic panels. At the transmission level, we would have a large field of photovoltaic panels. In other words, tremendous number of arrays, photovoltaic arrays that would generate a lot of electricity. And we might, because of the size of that, we would couple it into the transmission part of the grid. The other type of solar is concentrated solar power, CSP, where we have mirrors that reflect the sun to a boiler that's sitting up on the top of a tower, and it creates steam, and the ways we mitigate this, one would be batteries, right? Because you want your lights to be on at your home all the time, whether the sun is shining or whether it's not shining. So when that sun goes away, how do we generate electricity for your home? Because we don't have solar generation anymore, right? Well, instantaneously, the batteries can be used. Instantaneously, batteries can kick in, like lithium-ion batteries. But if it's a longer time frame, the batteries will eventually discharge, right? So we'll need to use things like I said, natural gas-fired, fast start, fast responding turbine generators. And then ideally, I mentioned we have an electronic gas hybrid turbine that we came up with at GE a couple of years ago. And it's 10 megawatts of lithium-ion batteries with a 50 megawatt natural gas-fired turbine generator integrated together in optimized operation with software, okay? So that's a way. But what's really cool, and I talked about this, and I talk about it in my article in Power Electronics Magazine, is low voltage network dynamic grid edge controllers. If you're really interested in this, you should read my article in Power Electronics Magazine, because you can find it online. And it's really unbelievable, the volatility. When you have a high penetration of solar panels on homes, and they're all on the same feeder, and when that sun all of a sudden is seen from the fog, the fog has burned away in the morning, and all of a sudden all these homes see the sun and they all start generating at the same time. You should see the voltage waveform. It just shoots up like a rocket. and then it oscillates over a wide range. And the poor distribution system is going crazy. The voltage is so volatile, you know, and you don't want that volatility at your home, because your light bulbs would be very, very bright and then very dim and then very bright and very dim. That tap changer is operating all the time as the primary voltage fluctuates to keep the secondary voltage constant, right? So you want to keep the voltage at your home constant, but the primary voltage, when it's that volatile, it causes tremendous operation of the tap changer, and that's why it's wearing out, right? So low voltage network dynamic grid edge controllers are low voltage power electronic controllers that do a great job of addressing that volatility on the low voltage network. We don't want that volatility to go up from the low voltage network into the distribution grid and up into the transmission grid. We want to mitigate, we want to address that low, at the low voltage network. And so we use these continuous set point controllers. One company that supplies these, if you're really interested in this, look at the website for a company called Varentech. V as in Victor, AREN, T as in Tom, EC. Varentech has these low voltage network dynamic grid edge controllers that work very, very well, and they're very inexpensive. They're grid edge controllers. We put them on the low voltage network, and they do a great job of continuous set point control, and they smooth out that volatility in the voltage. So these are, energy storage, natural gas-fired turbine generators, the integrated operation of batteries and turbine generators, and low voltage network dynamic grid edge controllers are some of the ways we do it today. Okay?
Thank you, sir. Thank you, sir. Sir, there's a question in the comment box. I will read it out for you. Rushikesh Deshmukh has asked how cyber security threats can be dealt in micro and distributed grid.
Yeah, I didn't mention cybersecurity yet, but we everything, and I can't say enough, everything that we do, cybersecurity is an important part of what we do from the very beginning. When we develop new technology, I actually have a PowerPoint slide that shows product development life cycle, and it shows the importance of cybersecurity in every step of developing new technology. Okay, so one thing is really thinking about vulnerabilities and how to address those vulnerabilities at every step of the development process. The second is with cybersecurity is training people to be more aware and be more careful with when you're online, when you're on your computer or your phone. If you look at many of the incidents that have occurred in the world, how those hackers were able to obtain the information they needed to get into the network was through people opening attached files, people clicking on links in emails that gave the hackers their account information, their passwords, their phone numbers, sometimes credit card information. So first step with cybersecurity is really people being trained to not click on links or not open attached files that you don't know the sender. You don't know what it's about. In all companies today, when you start working, like GE, my company, our IT department sends all the employees what we call a phishing email. PHISHING, PHISH, a phishing email. And they try to trick us, okay? They try to trick us to click on a link or open an attached file. And when we do that, our name gets on a list, and we're part of a training program on being more careful, okay? So all companies are training their employees to do that. And then the third thing is that all the technology we develop, a lot of it we send to a separate government lab, and they have their own hackers do penetration testing of our integrated systems to look for vulnerabilities and teach us as a supplier how to patch those vulnerabilities to have a more secure system, okay? So there's a number of things that we're doing today to try to be more vulnerable. I'll tell you what, I give a separate talk on cybersecurity, and I go through what happened in Ukraine, where the hackers planned the attack over a 9-month period. And then they launched the attack, and it caused 3 control centers and 3 distribution management systems to go down, and it caused 225,000 people to be without electricity for an extended period of time. I spend time and I go through the 25 steps that those hackers took over a 9-month period to plan the attack and launch the attack. And we learned a lot from that, and we're much smarter now as an industry and know what potential vulnerabilities are and how to address those, okay? So it's a never-ending process of continuous learning and doing more and more as time goes on.
Thank you, sir. That was really an informative section. I think all the queries are solved, so now we can move on to the feedback section.
It's time for feedback session. If anyone has any feedback about the session, you're welcome.
Sir, it was a great pleasure having you here. We all once again thank you for taking a wonderful class. Thank you.
Great. Let me say thank you very much, and I sincerely and truly wish you all the very best of success in your studies, with your families, in your lives. Take initiative. As I said, really do as much as you can to manage your career. Take leadership positions. Be proactive. Don't be reactive. Don't wait for things to happen, but take the initiative, right? Be proactive and do the most you can to be the best engineer you can be and the best person you can be, and really help as many other people as you can. Be the best friend a person can have, and in general, just the best person that you can be in life. Okay. So I wish you the very best, and thank you for the opportunity today.
Thank you, sir. Thank you, Abel, for the feedback. And now I welcome Dr. Radhakrishnan, sir, the principal of SNIT, for the event feedback. It's our honor to welcome you, sir. So please.
Am I audible?
Yes, sir.
Thank you. So, respected officials and dear participants, at the outset, I congratulate all the participants and the students in IEEE and SEEM to select this topic of current relevance. The initiatives taken by the students under the guidance of Assistant Professor Karthika Miss and Sarasar is exemplary. Special mention to HOD Lakshmi Miss also. I place on records my sincere thanks to Mr. John McDonald, who could elevate the aspirations of the attendees with his outstanding delivery. As a civil engineer, it was an eye-opener to me also, and it helped me to understand that around the world, a change in electricity generation is desired in order to fight climate change and increase energy security. He mentioned the need of bringing down the percentage of carbon emission and enable the customers to save money without compromising their lifestyle. That is the most valid point I noticed. I believe that in recent years, utilization of renewable energy resource in smart grid system has been increasing. It was interesting to note that the comparison of old grid with smart grid. A significant number of programs have been implemented in various parts of the world. Most of them are in developed and developing countries. Some studies show that these technologies can provide reliable and comparatively low-cost electricity service. The increase in renewable energy or generation is an inflexible system is the major challenge for the developers and practitioners of the grid system. The webinar was the need of the hour, and I am happy that all the participants received it well and realized what's going on in the world around you. We are lucky to have a person like Mr. John McDonald as our resource person today and to keep this evening a memorable one. Thank you, sir. Thank you for giving me an opportunity to tell my opinion frankly. Thank you. Thanks a lot.
Thank you so much, sir, for your valuable words. And once again, I would like to welcome Dr. Radhakrishnan, sir, to present our venerated speaker with a memento as an expression of our gratitude.
Sir, John McDonald, sir.
Yes.
With all our appreciation, with all our love, we are presenting it to you. Please accept it, sir, with gratitude. I, on behalf of all the participants, submitting to you. Please accept this.
Thank you very much. Yeah, thank you.
Thank you, sir. Thank you so much, Radhakrishnan, sir. And on behalf of everyone, we would like to thank our honorable speaker, Mr. John McDonald, sir, for your time. And moving on to the next section.
Now I welcome Head of Electrical Department, Mrs. Lakshmi Ma'am, to hand over the Certificate of Appreciation to our speaker, Mr. John McDonald, sir. We are very much honored to welcome you, ma'am. Ma'am, please.
Thank you all. Good evening, all.
Yes, sir. Yes, ma'am.
This was a great session by Professor John McDonald. I think this session was seen by more than 500 students in online mode, and he discussed his experience with IEEE, how IEEE helped us to develop leadership skills, how IEEE helped to address technological deficits, which is indeed a big problem nowadays for the fresh graduates. He also showed the influence of IEEE in societal trends. It was really a great informative session for all of us, sir. And actually, it was great to hear all this from an esteemed person like Professor John McDonald, who have 50 years of experience with IEEE. He also shared a lot of new knowledge on grid modernization, smart grid holistic solutions, smart meters, rooftop solar PV systems, etc. I take this opportunity to congratulate Professor John McDonald for his excellent presentation. We would like to have more sessions from you again. As a token of appreciation, I'm virtually handing over the Certificate of Appreciation to you, sir. Thank you.
Thank you. You know, I'd be happy to do some additional talks for you at any time in the future. Just let me know. I'd be happy to.
Of course, sir. Thank you, sir. Thank you so much. Thank you, ma'am. Now I invite Ms. Avarna Mall, Vice Chair, IEEE SPS SNIT and IEEE IAS SPS SNIT for the word of thanks.
Good evening to one and all. As all good things comes to an end in life, so is this session. It's really great that this program has turned out to be very successful. I, Avarna Mall, Vice Chair of IEEE SPS SNIT and IEEE IAS SPS SNIT, it's a matter of pride for me that I am proposing the vote of thanks for this session. On behalf of my colleagues and the entire IEEE and SEEM student members, first of all, I thank God. I want to thank our chief guest, Mr. John McDonald, Smart Grid Business Development Leader at CIGRE Solutions, CIGRE Distinguished Member, IEEE Life Fellow, Past President, IEEE Power and Energy Society. Thank you, sir, for an informative and profitable session. Next, I would like to thank our principal, Dr. Radhakrishnan R, for his great support for the conduction of this program. Thank you, sir.
Thank you, Avarna.
Next, I want to thank our branch counselor, Ms. Karthika Nair ma'am, and chapter advisor, Ms. Sri Lakshmi Nair ma'am, for presiding over the event and motivating and inspiring us at every step. Thank you, ma'am. Next, I would like to thank our SEEM faculty coordinator, Assistant Professor, Mr. Sharad Kumar S, for his great support. Thank you, sir. A special thanks to the organizing committee and teachers for the influencing support and coordination. And last, not the least, my heartfelt thanks to all who actively participated in the session. Hope you all have enjoyed it. Be safe and wear masks and take protective measures against COVID-19 pandemic situation. Stay safe. Thank you.
Thank you, Avarna. Now, I request all the participants to turn on their video to take a screenshot. Thank you all.
So it's time to conclude our session. Now all participants can fill the feedback form provided in the chat box. Let me conclude today's session by thanking everyone who participated in this session and making it a great success. Now we are winding up our session. Wish you all a nice day.
Once again, thank you to our honorable speaker, Mr. John McDonald, sir, for your time. Your presence has been very valuable to us today, and we certainly look forward to another interaction in the near future. Thank you so much, sir.
Thank you. Thank you, everybody.
Thank you, sir.
Thank you, sir, for joining.
Thank you, sir.
Thank you, sir.
Thank you so much, sir.
Now all the participants can leave.
Thank you, sir.
All right. Bye-bye.
Thank you so much, sir.
Thank you.
Thank you, sir.